Near-field optics started with as near-field microscopy actually for me, it was the call for the announcement of the first conference on near-field optics that took place in France, in Arc-et-Senans. I think it was back in '92, and at that time I had no idea what it was. I just learned that there was a new technique able to do imaging microscopy with sub-wavelength resolution. And that was absolutely fantastic to me. I wanted to understand what that was. And I was particularly interested because since I had some background in theoretical electrodynamics, scattering of light, I thought I could understand that. So I was extremely interested. At that time I was working on light scattering, mostly scattering by gratings. And that involved plasmonics. Plasmonics was already a very trendy topic in the 80s. That was well before it became plasmonics. It was about surface plasmon excitation. The word plasmonics didn't exist, but this excitation was changing a lot the properties of reflection by structured surfaces, rough surfaces. So diffraction by gratings and also scattering of light by rough surfaces. At that time there was something very exciting that was Anderson localization. People were looking at Anderson localization with light. The idea was that photons do not interact, so it's a simpler, better system to observe localization. And some related phenomenon was the backscattering enhancement, also called weak localization. So that was mostly my field. Scattering is a topic where optics people and physicists are not as good as electrical engineers, particularly when it's in the 80s, when it's about solving real problems using numerical simulations. The electrical engineering community was far ahead as far as numerical simulation was concerned. We're talking about the mid-80s, okay? So computers were not what they are nowadays. So I attended conferences in the electrical engineering community to learn how to solve Maxwell's equation using developing numerical solutions. I was also involved in the optics community. Apart from that, something very particular in my case was that I was also interested in the absorption and emission by surfaces. So this is relative transfer theory. So this is mechanical engineering community. So it was really at the intersection between physics, electrical engineering, and mechanical engineering as far as heat transfer, radiative heat transfer is concerned. At that time, I totally moved into near-field optics. That became really my first topic in the mid-90s until 2005. And in the meantime, many different communities merged. So before 2000, we had photon and crystal community, we had semiconductor communities, quantum dots communities, both colloidal quantum dots, mostly chemistry, people from semiconductor physics doing epitaxially grown semiconductor, and also, of course, my initial community, which is near-field microscopy. So all those communities merge, and that became Nano-Optics. And 2005 is really a moment where we started having conferences with all these people merging, talking together. And this is more or less when plasmonics, the name plasmonics, was invented. I think it was during the postdoc of Mark Brongersma with Harriet Water in the 2000 something. And that was a revival of plasmonic for two reasons. One, you could fabricate structures with very good control, and the second reason is that you could observe directly the fields in the near field. You could see these surface plasmon. Back in the 80s, when we were looking at plasmons, it was far-field scattering. It was a spectral signature on the reflection spectrum. You couldn't see them directly. In the early 90s, really, the understanding of the mechanism of how an image with sub-resolution was produced, that was really an issue. Actually, most conferences on near-field optics, they had a session on contrast mechanism. So really, people were trying to understand. They were producing images, but most of the time they had no idea those images, how they were related to the properties of the samples. That was a big issue. There were also some scientific misunderstandings associated with this vagueness of what these images were. One of them was, that was in the very beginning. Is the interaction with the tip a necessary condition, or can the tip be a passive probe? And is it possible to still have super resolution if the tip is passive? The answer is yes, of course, but that was not very clear at that time. There was another fundamental issue with reciprocity. The very concept of evanescent wave, which is a standard theoretical tool nowadays for everybody in near-field optics, that was perfectly well understood in the electrical engineering community and not at all in the optics community. And there were some wrong ideas like evanescent waves do not fulfill reciprocity, for instance. That was a commonly accepted mistake in the community. So we had to fight at that time with referees, I remember. Particularly this about reciprocity, the one I just mentioned. And another one which I can add is if you have a dipole with a fixed amplitude, fixed dipole moment, then what everybody learned in school is that the power emitted by the dipole is fixed and depends on the dipole moment, which is not true. It depends on the environment. And people are starting realizing that during these years. The scope of metamaterial is so broad that there cannot be a single answer to that question. You had to split what you mean by metamaterials. Metamaterials covers basically a large part of the electrical engineering activity today and also of physics and material sciences and so on. So it depends. In some cases, metamaterials are already a reality. For instance, you are designing antennas, you can fabricate and sell antennas. It's already a commercial product. In structural mechanics, metamaterials is absolutely reality. You can find metamaterials everywhere, and everybody is using materials which are actually metamaterials. As far as optics and quantum optics is concerned, we are totally in the field of research. So we really have to specify what we mean by metamaterials. But definitely in terms of quantum metamaterials, there are many challenging issues, and this is definitely still a research topic. What are the coherence? How do we control the losses, the quenching? How do we control the coherence? When we move, what is under control and well understood nowadays is the interaction between a single emitter and a nanostructure. I think we have made tremendous progress for that. If now, instead of having one emitter, you put only two, you start having problems. And if you put 10, 50, hundreds, so you enter the mesoscopic size, and this regime, this is still something we don't know much about it. I'm not sure. I think it was around the year 2000. I suspect that there was a movement from near-field optics to nano-optics. I suspect that this definitely it was around 2000, and I believe it was related to the Nano initiative in the US. The US government decided to inject a lot of money in nanoscience, and I guess the optics community, like other optics communities, needed to benefit from that, so they needed to introduce nano-optics. So I guess that we would find that there is a correlation with the Nano initiative in the US if we were digging seriously. Obviously, the understanding of the process of imaging, that question has been one of the key questions. that was a major step to understand the real mechanism and to come up with a model of near-field imaging. This is for the near-field microscopy, so which is only a sub-part of this near-field optics community. So I guess we should look in detail at different structures, the different sub-communities. One of the key issues, I believe, is the introduction of the concept of antenna in optics. This is a milestone. And the next step was to recognize that these antennae, when they are resonant, they are actually cavities, and you can plug into this concept everything that has been learned before in cavity QED, cavity quantum electrodynamics, where the cavities were non-lossy, so there are big differences. But however, all the concepts still apply. And exactly to understand how they apply and how you combine them with losses, to a large extent, this has been achieved already, and that has been a tremendous progress. But the list is much longer. On a more general form, I could rephrase in terms of interaction between nano-optics and quantum optics. This is definitely, this intersection is, I guess, one of the big challenges for the next 10 years. There is still a lot to be done in terms of concept, in terms of theory. I think the most challenging issues are really theoretical more than numerical. Of course, we always need improvement, but my understanding is that the key questions are theoretical questions. Of course, you can write a master equation and try to solve it, and take a system which is bigger and bigger and bigger. The key issue is to come up with a simple picture of what's going on, identify the right concept, and be able at the end of the day to say how you could design a system and why it would be coherent or not. And I mean quantum coherent. What is decoherence? How can you control decoherence? And what you should do to control decoherence. That goes beyond writing a big equation trying to solve it by brute force. Yeah, I mentioned that quenching is definitely an issue. So when you have metallic structures and emitters, quantum emitters, controlling the losses is definitely an issue, and this is a hot topic. It is important because during some time we thought that there was no way to address this issue, and it seems that we can circumvent losses to some extent. So definitely this is a big challenge. The other challenge definitely is about mesoscopic systems, so looking into interaction of small ensemble of emitters, quantum emitters coupled to nanostructures. I think this is certainly one of the big challenges.